We will now talk about the energy associated with the signal and the power associated with the signal. And based on this, we will be able to classify signals of either as of the energy type, or energy signals, or power signals, or sometimes neither. Okay. Now let's begin this section by assuming that we have a signal. Actually, we have a real signal x of t. And let's think of the signal x of t as actually the voltage that is applied to a resistor of 1 ohm. Okay, a resistor with resistance 1 ohm. So x of t is actually the voltage, and you have a resistor which is 1 ohm. So the power that's dissipated in the resistor at any time, it's going to be the square of the voltage divided by the resistance, right? And the resistance is 1 ohm, so the power at any time, or we're going to call this as the instantaneous power, is actually v squared, x squared of t, right? So since this is a signal that lasts for a certain amount of time, the total energy that is dissipated is the integral of power. So this is integral x squared of t dt if the signal exists in general from minus infinity to plus infinity. So then it's integral minus infinity to plus infinity of x squared of t dt is the energy that's dissipated across a 1 or in a 1 ohm resistor. Okay, so we're going to call this as the energy associated with the signal, and I'm going to call this as Ex. Okay, E refers to energy and X refers to the fact that we're talking about the signal X. Okay, so our definition of energy associated with the signal is simply going to be integral negative infinity to plus infinity x squared of t dt. Okay, actually from now on it will be useful for you to abstract the notion of the energy and not have to actually think about x being a voltage signal. Okay, x does not have to be a voltage signal, it could be anything we can think of. We're going to call this integral as the energy associated with the signal. Okay, I talked about this electric circuit just as a way for to motivate why this may be reasonable to think of as the energy associated with the signal, but it's really another way to think about this is to actually think of this quantity as a measure of how big a signal is. What do I mean by that? Now, what I mean by that is, if you have two signals and you want to compare them in terms of which of the two signals is bigger. I mean, we have two functions of time, right? So here is a signal x1 of t, and let's say we have another signal x2 of t. Suppose I want to know which of the two signals is bigger. Now it seems like there are, first of all, I mean, it doesn't even seem to make sense. What do we mean by one signal being bigger than the other, right? But what we're going to do is this: we're going to think of the energy associated with the signal as a strength for the signal, and based on this we're going to define, or we're going to find out which one is bigger than the other. Of course, this definition, or using this particular definition of energy to decide which of the two signals is bigger, is completely arbitrary. Okay, you could actually have defined something else, for example the maximum value taken by the signal, or the absolute value of the, or the maximum of the absolute value, or integral of the absolute value, or anything like this. And at this point it's just an arbitrary definition of something which will be used as a measure of the strength of the signal. Okay, you will see later that this kind of a definition comes somewhat naturally in some contexts, and it's actually useful Um, but let's not talk too much about that at this point. This point we'll just leave it as saying the energy associated with the signal is simply defined by the integral shown here. Now, we will use the same kind of definition even when the signal is not a real signal. Suppose x of t is a complex signal. We're going to define the energy of the signal as integral minus infinity to plus infinity, the square of the magnitude of the signal. Okay, pay attention to the magnitude symbol here. A common mistake students do is to forget this magnitude sign here, and when x of t is complex, if you forget the magnitude sign, x squared will be a complex quantity, and then you will have an integral of a complex quantity which in general is complex, and you will end up with the energy being a complex number. And you know that you're making some mistake if you end up with the energy being a complex number. Okay, so you can actually think of this as the more general definition of energy, because if x is a real signal, the magnitude of x is just the same as, or the square of the magnitude of x is simply the square of x itself. Okay. The same thing works for discrete time signals as well. So if x of n is a discrete time signal, then the energy associated with the signal is, the integral now becomes summation, of course, magnitude of x of n squared. Okay. All right. Now, what is the power associated with the signal? Now, power is energy per unit time, right? Or we can think of this as the average energy per unit time. So then, of course, the question then is this. Let's say I have a signal. The average energy per unit time for this signal can be computed as follows. So what we can do is this. We can take a window from time minus t to plus t. Okay. We can compute the energy, which will be over this block, it will be minus t to plus t, integral magnitude of x of t squared dt. But I'm interested in the average of the power, right? But so the average will be this multiplied by 1 over 2t. Okay, but now notice that this quantity can actually change depending on how you pick your capital T. So we define the power of the signal p sub x as actually the limit of this quantity as t tends to infinity. Okay, so basically what we are saying is, well, we're looking at a very large window in time from minus t to plus t, and you're computing the average energy within this window. Okay. In the discrete time case, so this is in the continuous time case. In the discrete time case, we'll use the same definition. So what we have here now is, you have a discrete time signal which has something like this, which does something. So 0 is somewhere here. You're going to take a window from minus n to plus n. Okay. I'm just throwing in these minus n's and plus n's somewhere in there. I'm not actually sure that there are the same number of samples on both sides. Okay. All right. So then we can, what's the energy over this time window? The energy over this time window is actually minus n to plus n, sum of there is no integral. This should be a summation. From minus n to plus n, a magnitude of x of n squared. But I want to average this, right? So how many samples do I have from minus n to plus n? Be a little bit careful. It's not 2n, but it's 2n plus 1. Okay, so this is a strange thing that happens with discrete time signals. Um, with continuous time signals, you don't really see the 2t plus 1, so be a bit careful. It's because we are counting the exact number of samples that you have from minus n to plus n. You're going to end up with 2n plus 1, and then you take the limit of this as n tends to infinity. So that will be the power associated with this discrete time signal. Okay. Okay, let's work out a few problems here. Or actually, maybe before we work out a few problems, we should probably talk just a little bit about the power of a periodic signal. Let's say power of a periodic signal. So we can do both the discrete time and the continuous time cases at the same time, and you're going to see it's not all that different. So let's look at the continuous time case. Suppose we have a signal x of t, which is suppose we have a signal x of t, which is a periodic signal with time period t naught. So what does this mean? This means that the signal actually repeats itself every t naught, right? So here is an example of such a signal. This is t naught, this is minus t naught, so on and so forth. What can we say about the energy of the signal? You may want to pause for a minute and then think about this. What is the energy of the signal? Well, the energy of the signal was defined as the integral of the square of the magnitude of this signal. And the square of the magnitude is non-zero over every period of the signal, right? Okay, so the energy associated with this signal is infinity, right? The power associated with the signal, on the other hand, is the average of the energy. And since the signal repeats itself, it's enough for me to look at any one period of the signal and then take the average over just this period, because the same thing is repeating over time. So the power associated with this signal can be thought of as 1 over t naught integral from, let's say, 0 to t naught of this signal, right? Notice that you don't need any limit anymore, because the same part, I mean, the signal just repeats itself every t naught, so you could just look at any one period of the signal. And notice that since you can look at any one period, you actually do not have to integrate from 0 to t naught. Rather, I could have actually chosen any one period of the signal. You know, I could have chosen something like this, for example. No, not here. Could have chosen something like this, right? I would get exactly the same value. So what I could say is I could choose any small t naught and then integrate from t naught to t naught plus capital T naught of the magnitude squared of the signal. Often what you want to do is you want to choose the small t naught so that it makes your integral easier to evaluate. That's really all it is. And in the same way, the power associated with a discrete time signal can be thought of as 1 over n naught summation over any n naught to n naught plus n naught minus 1 magnitude of x of n whole squared. Okay. And notice that this is n naught to n naught plus n naught minus 1. That's really what constitutes n naught values, right? All right. And that's about it. That's pretty much all I want to say about energy and power at this point. And we'll work out a few examples. I'm going to work out a few examples so that hopefully these concepts get clear. I'm going to stop the video here and then make another video link for the examples.